can do anything proper with numbers, complex operations, apply definitions to them, that sort of thing, it's important that we have a way of working with them. It's important that we can read them and be sure which number it is that we're looking at, which number it is that we're working with. And it's important that we can compare numbers, know how to put them in order, for example. Which one is smaller, which one is larger, where numbers would go. Now, the first of these big top tips is the number line. Now, I'm a big fan of number lines because they're a nice visual way to see where numbers fall. And once we're confident in reading numbers, once we're confident in putting numbers in that order, having this idea of a number line in our heads, for example, is a very useful thing. In particular, you could always draw your own number lines. There is plenty of empty space on an exam paper where you could quickly draw a short number line just to give you an idea. And we will see lots through the year that number lines will crop up. Number lines will be useful for various different things if that's the kind of way you think about things. It's also worth pointing out that you have a ready-made number line because you will have on your desk one of these. And what is a ruler if not a number line that runs from 0 to 15? Just because a ruler is designed for measuring, and that is obviously something we're going to use it for later on, just because a ruler is designed for measuring doesn't mean that you can't also use it to count on. We could easily count from 0 to 1 to 2 to 3 and so on up to 15 through those first 15 standard counting numbers. Now, the problem with using a 15cm ruler or even a 30cm ruler as a way of reading numbers, of working with numbers, is fairly obvious. It only runs to 15 or 30. There are obviously many, many more numbers than that, and we might need to be able to work with them, put them in order, read them correctly, that sort of thing. Consider, for example, the number 35. Now, we know that that number is 35. It's not a 3 and a 5, it's a 3 and a 5 working together to give us the number 35. And we know that that number is 35. How do we know? Because that there is a 5. And we know that this 3 is not really a 3, it is in fact a 30. So a 30 and a 5 working together to give us 35. If I were to add an extra digit in front, for example, then we could have something like that. 435. Well, we know it's not a 4, a 3 and a 5. We know that that is a 4 representing 400. With the 3 representing 30 and the 5 representing a 5. 435. Alternatively, I might have put a number on the end rather than at the beginning and put a number here like this, say, in which case the values of the numbers there change. It's not a 3 representing 30 anymore, it's now a 3 representing 300. The 5 is no longer representing just 5, it's representing 50, and the 8 on the end is simply an 8, to give us the number 358. Now, this idea of the values that digits take, the values that numbers take as part of bigger numbers, is one of place value. And this idea of place value is what we're going to use to help us read and write numbers correctly. Now, to be able to do that, we're going to pull out a good classic primary school tool, which is the hundreds, tens and units grid. We're going to draw a grid, and we're going to use that grid to help us read and write numbers according to their place value. The smallest value of number, the smallest column, is the units. So we're going to have a U for units. If we go a place value up, tens. Hundreds getting one bigger, because 3-digit numbers would be hundreds numbers. Next one up, thousands. 10,000, so tens of thousands. Hundreds of thousands, and then millions. There are numbers bigger than that. We can have 10 millions, 100 millions, and then billions, but this is what we're going to stick with for now. Units is the smallest, tens, hundreds, thousands, 10,000s, 100,000s, and millions. And if we were to write any whole number in that grid, we could switch between the numerical version and a more written version by reading off what we've got. For example, if we wanted to write this number in our grid, something like this, say 4327, we could read off the value of those numbers in the column. So we have 4 in the thousands, so that's 4,000s, 3 in the hundreds, so that's 300, 2 in the tens, so that's 20, and then 7 in the units is just 7, so 4,000, 300, and 27. And in fact, that is a perfectly reasonable 1-mark question. Here is a number in figures, 4327. Write that number in words, 4,327. That's a fairly straightforward example. They could be more complicated, they could have more digits in than that, but a nice straightforward 1-mark question. It's worth saying at this point, it is a maths exam, not an English exam. Any reasonably decent spelling will do. You do not necessarily have to spell the word thousand or the word hundred or whatever correctly, as long as you've made a reasonable attempt towards that, and your attempt looks like it's supposed to be the word thousand or hundred or whatever. Obviously, if you're trying to write the word thousand and you write the word sausage, that's not going to be acceptable. But any reasonable attempt will do. Now this also works for larger numbers. If we were to have something like this, say, $239,402, well, first thing we could do is we could look at how many thousands we are dealing with altogether, and that's altogether. We are getting a thousands contribution from this number here, the 9, because it's in the thousands column. We're also getting a thousands contribution from the 3 here in the 10,000s, and we are getting a thousands contribution from the 100,000s. What number is in that box there? 239. 239. 200,000s and 3 10,000s will be 30,000 and 9,000s. Alternatively, 239 is, if we ignore the rest of it, 239. So that's 200. And 39,000, and then the rest of it 400, no tens, so just 402. We don't need to write and no tens, although if you do, technically it's not wrong. It feels like an obvious thing to say, but it's worth pointing out anyway. When you are writing a number in words, make sure that you are actually using words. Do not, and it's easy to do, it's easy to fall into this trap, write something like 435. That's not words, that's words and numbers. Again, it feels like an obvious thing, but people do it. It's easy to forget, it's easy to fall into that trap, and then you've thrown away a mark. These kind of questions also work the other way around. You could be given a number in words and then asked to write it in digits. For example, the number 1,759,425. In which case we would have 1,759,425. 1 in the millions column, 759 being our thousands contribution, so that needs to go across the 3 thousands columns, 425. It's also worth saying with a question like that you don't necessarily have to fill the digits in order. If you were to look at what you've got, well, you could confidently put the 1 million in there. You could confidently put the 425 in there. The 759 have got to go somewhere. There are 3 empty columns. They're going to have to go in there. Then 7, 5, and 9 to give you the 759,000. Now the problem with this grid as it stands, millions, hundred thousands, 10,000s, thousands, hundreds, tens and units. The problem with this grid as it stands is that it only allows for whole numbers. But we know from life that whole numbers are not the only story. Think about, for example, money. Well, you could have something like £4 and you could have something like £5. They are both whole values of pounds, 4 whole pounds, 5 whole pounds. But actually we know that there are a whole load of other numbers, other values in between those two figures. Think about the ruler again. On the ruler, we've got 0 centimetres, 1 centimetre, 2 centimetres, 3 centimetres, 4 centimetres, and so on. The whole numbers of centimetres, but there are also all these little lines in between, all these little values in between 0 and 1, between 1 and 2, between 2 and 3, and so on. We talk about shoe sizes, whole numbers of shoe sizes, shoe size 7, shoe size 8, shoe size 9, but you could also be shoe size 7.5, 8.5, 9.5. And the problem with these numbers is that they won't fit on the grid. If we were to try and write something like 4 and a bit, well, the 4 could go on here, but if we wanted a price like, say, £4.25, well, where's the £1.25 going to go? The 4 would have to go in the units because that's what 4 is. It is 4, not 40 or 400. If we put the 4 anywhere else, it would become a bigger place value. We need some way on our grid to show things like that. Not just money, but money is the classic example. We need some way of making it possible on our grid to show those 4 and a bit numbers, or whatever. Those, what we call decimals. The problem with decimals is that they are very difficult to explain. It is very difficult to explain to you what a decimal is. So in fact, for now, we are just going to treat decimals as and a bit. A whole number and a little bit more, but not quite enough to get up to the next whole number. Like this. There is a whole number. There is the next whole number up. Here is 4 and a bit, but not quite enough of a bit to get up to 5. In the weeks to come, we will pin down a little bit more accurately what these decimals are. But as far as you need to know at the moment, they are and a bits. They are the things that happen between whole numbers. And again, we will pin down more properly what they are. So what we're going to do is we're going to extend our hundreds, tens and units grid. We're going to start off with the same grid as previously. Millions down to the units. Millions, hundred thousands, 10,000s, thousands, hundreds, tens, units. And then we're going to put in this split. This is the end of the whole numbers. So we have a particular symbol to show that that is the case. And we do a dot. And that dot, or a full stop, whatever you want to think of it as, is called the decimal point. And all the decimal point is the split between the whole numbers here and the decimal part, the and a bit part here. And it's just a physical split point. Then we have the first column down on the decimals. The first column of the decimals is called the tenths. I'm going to write that as this. The next column down is the hundredths. And then the next column down would be the thousandths. If there was another column, 10,000ths, 100,000ths, millionths, and so on. You may be wondering why they are called tenths, hundredths, and thousandths, and you may also be wondering why there isn't a unitths. These are all questions that we will answer in future weeks. For now, just take it as given that they are called tenths, hundredths, thousandths. There are also easier ways to write these. You might see this written as 1 over 10. You might see this written as 1 over 100, and you might see this written as 1 over 1,000 with lines in the middle. They are, again, all perfectly valid. They do mean the same thing, and in future weeks I will explain why. But we're not going to go anywhere near that just yet. We're going to focus just on the names for now. Tenths, hundredths, thousandths. And actually, it doesn't really matter what the names are, because they just function in the same way as these other columns. They are all columns as part of the whole grid. And actually, this is the whole grid that we're going to use. Because this grid will let us write any number that's within the size that we've specified in the grid. Obviously, we could extend the grid further up or further down to have the 10 millions or the 10 thousandths if we wanted. We're not going to. This will do us for most numbers that we might need to come across. Now, why this is useful, we can now write bigger numbers in here. If we were, for example, to write this number in, 1, 2, 5, 7, 1, 5, dot, 8, 6. First thing to notice, the dots line up, the decimal points are in the same place. Now that will be true of any number. Whenever we're putting any number in the grid, the decimal point is a good marker. If we line up all the decimal points, all our numbers are lined up correctly. Next thing to notice, there are no random gaps in the number. Once the number has started, every column is full until it finishes. Now it might be full with a 0, but it's still got something in it. We don't have random gaps in the middle of numbers. Once we start a number, there are no gaps until we finish the number, and if there isn't anything in the column, then we put a 0 in to show that there is nothing. In this way now, we can read off the whole number. So first of all, let's deal with the thousands like we did before. So we've got 1, 2, 5, or 125 across those 3 thousands columns, so that must be 125,000. We also have then a 7 in the hundreds, so 700. And we have 1, 10 and 5 units, so 15. And that's the whole number part, 125,715. We need to show the decimal part as well. So we're just going to simply write the word point, because that's what it is. 125,715 point, and this is a slightly different bit. We're just going to write them as digits. 8, 6. Not 86, because that isn't an 86. It's an 8 and a 6. It's an 8 tenths and a 6 hundredths. What does that mean? Nothing particularly, other than there is an 8 in the tenths and a 6 in the hundredths. But just for convention, just because that's how we write it and how we read it, we're going to read it as 0.86, not as 0.86. Because we're going to try and distance ourselves from thinking that that is an 86. It isn't. To be an 86, it would have to be in the tens and the units, and it isn't. It's in the tenths and the hundredths, so 0.86. A little aside on writing numbers in digits. Take the number 4,328. I would write that as simply 4328, using my hundreds, tens, units grid, my thousands, hundreds, tens, units columns, 4328. Some people, however, might prefer to write that like this, with a comma after the 4,000. 4,000, 328. Particularly with bigger numbers, you might see these commas turning up. Something like a million, say, you may see written like that, although I am far more likely to write it like that. Either with the numbers all one after the other, or perhaps with a small space in between each of those, but only small to show that it's still part of the same number. This idea of writing commas in numbers is quite hotly contested and is quite argued over. Generally speaking, if we're doing maths properly, and I use the word quite loosely, if we're doing maths properly, without the comma is better. This one and this one are the better ways to write those numbers. For one very simple reason. In parts of Europe, rather than use a full stop to show a decimal point, certain parts of Europe use a comma. So now as soon as you're using a comma in numbers, are you meaning this to be 4,328 or are you meaning this to be 4.328? And it depends who's reading it. So to avoid this ambiguity, to avoid this chance that something could be read wrong, because maths of course is all about accuracy and about setting up a common system, a common language of notation that everybody can use, properly we shouldn't be writing the comma. If, however, in an exam you put the comma in, it will just be ignored. No one is going to mark you down for it. No one is going to criticise you for putting it there. It's kind of personal preference, but with the knowledge that maybe be careful, just because out in the wider world, away from an exam, the comma can be used as an alternate way of writing a decimal point. Now, the particular beauty of this hundreds, cents and units grid, among the many things that it's useful for, it is particularly useful for really getting to understand how these decimals work, in particular in putting them in order. For example, if I was to ask you which was bigger, 1.8 or 1.08, we could use the grid to help us work that out. 1.8, 1.08, we're looking at them, they are in fact very similar. But if we were to put them in the grid, well, we can use the decimal point as a good way of lining them up. 1.8. If we were to put them in the grid, well, we can use the grid to show that they are not necessarily as similar as they look. We can really understand them if we put them in the grid. We can use the decimal point to line up where the numbers should go. So the first one, 1.8. 1 in the units, 8 in the tenths, and the point in the middle. And we know that's where they go. The point lines up. The 1 has to come before the point, the 8 has to come afterwards. The 1.08. Well, again, we've got the point, we've got the 1 on the left, and then 0, 8, one number per column, because that's how this grid works. We can only have one thing in a column, 1.08. And again, they still look fairly similar. But now that they're in the grid, we can compare them one column at a time. It is important to point something out about the columns at this point. The columns over here, the place value of the number is bigger than the columns over here. As in, the columns get bigger in value in this direction. As we go up the columns, the value gets bigger. A 1 in here, for example, is smaller in value than a 1 in here, which is smaller in value than a 1 in here, than a 1 in here, and so on. So as we go up the grid, up the columns, the value gets bigger, which means as we're going down the columns, the value gets smaller. That means the further right a column is, the less contribution it's making to the whole number. That means the further to the left that a number is, the further up the grid, the bigger a contribution a digit is making to a particular number. The further to the right a number is, the smaller the contribution the digit is making to the overall number. That means we can compare things one at a time. So we could start with the biggest value number in there, the biggest value digit. We could start with the 1, for example. Now in the first number we have a 1, in the second number we have a 1. They are exactly the same. Neither one is obviously bigger than the other. We have 1 unit here and 1 unit here. So there's no real comparison point there. But we could look at the tenths. And if we look at the tenths column, whether we understand what tenths are or not, it doesn't really matter. It's a column in the grid. And here we have 8 of these tenths, whatever they are, and here we have none of them. And 8 of them is more than none of them. Again, whether we understand what they are or not, we have 8 of something here and none of something here. So this suggests to us that the 1.8 is bigger, because it has more tenths. Yes, there are some hundredths here. How many hundredths are there here? Well, there's nothing in that column. If we wanted to, we could fill that column in. There's nothing wrong with that. We could put a 0 there. Has it changed the number? Well, here, without it, we had 1 unit, 8 tenths, and that's it. And here we have 1 unit, 8 tenths, and no hundredths. Well, in having none of something, we've not gained anything. It is in fact exactly the same number. We've just written it in a slightly different way. Now looking at those two, I would say it's even more obvious that the 1.8 is bigger. We've got 1.08 and 1.80, if you like, to bend the rules slightly on how we'd read that there. And 1.80 is bigger than 1.08. So the 1.8 must be bigger. Again, because it has more of these tenths. Yes, there are some hundredths in the second one and none in the first, but so what? Hundredths are smaller than tenths. Again, you don't need to understand tenths and hundredths to know that. You just need to recognise that as we move down the grid, the value in the column gets smaller. And as we move up the grid, the value in the column is bigger. One final way we could compare those two numbers, and that's to recognise that actually we all know something about decimals from real life. There is a place in real life where we all use decimals all the time without really thinking about it, and that is in dealing with money. So why don't I, in a different colour to prove that it's not permanent, just add a pound sign in front of there and make that £1.08. And why don't I add a pound sign in front of that one there and make that £1? Ooh, and hopefully we notice something a bit weird about that, because something doesn't look right about that first one. But we could add something to it to make it correct. What's wrong with it, first of all? Well, when we deal with money, we usually, and in fact always, have two numbers after that decimal point. We use the tenths and the hundredths, always. We use both. So I could add a 0 in there. Why a 0? Because we have got no hundredths. Exactly the same reason as before. I've not changed the value of the number, I've just made it look a bit more correct. And in comparing those two, we've now got £1.80 versus £1.08. Any way you look at it, the 1.8 is bigger and the 1.08 is smaller. Now we could take that kind of question to its logical extreme, and we could have a question like this one, for example. Put the following numbers in order of size, smallest to largest. 3.44, 3.04, 3.4, 4.3 and 3.404. Now your first thought with that question might well be, oh my, those numbers all look very similar. It's a little bit confusing. Well, that's exactly the point. They've been deliberately chosen so that they are all of similar size and so that they all look similar. They all use 3s and 4s and some of them use 0s as well. Because this question is designed to really test your understanding of place value. Now, I agree, they do look quite confusing, written there like that, as a list. But what if we put them in the grid? Now our first step is going to be just that. We are going to put them in the grid. We are not going to do anything complicated with them yet. We're not going to try and reorder them. We are just going to write them in the grid, in the correct places, lining them all up properly, in the order that they are already in. Because once we've done that, then we can work with them. We're not going to try and second guess ourselves, we're not going to try and reorder them, we're just going to write the 5 numbers in the grid in the order that we're given them. And the decimal points will help us. So first of all, 3.44. Well, there's a decimal point, 3 in front, 4 and 4 after, 1 number per column, 3.44. The next one, 3.04. The next one, 3.4. The next one, 4.3, and then 3.404. So for this one, we've gone into that thousandths column as well. So all I've done is I've written 5 numbers in the grid in the order I was given them. Because now what I can do, like I did with the 1.8 and the 1.08, I can compare these numbers one column at a time and look for which is obviously bigger, which one is obviously smaller, that kind of thing. And I can start to fill in the answer. In fact, I'm going to set up a space for the answer. I'm going to set up 5 spaces for my 5 numbers. So I can then write these in as I work out where they'll need to go. Smallest here, largest here, and then the other ones in between. So first of all, I'm going to look at the units. I'm going to choose the column with the largest place value, because that's having the biggest contribution to the number overall. I'm going to look at this. I've got 1, 2, 3, 4 of the numbers with a 3 in the units, and one with a 4. Now that 4 is obviously bigger than the 3's, so a 4 and a bit is obviously going to be much bigger than 3 and a bit. So the 4.3 must be my biggest number overall, so that can go in the last space, 4.3. Now we've used the 4.3, we can cross it off, we don't need to use it anymore, it's already in. But the units There's nothing else in there that's obviously smaller or bigger than any of the others. They're all 3. They're all the same. So we need to look at the next column along and see if there are any differences there. We need to look at the tenths. Now looking at the tenths, we've got 4 tenths, no tenths, 4 tenths, and 4 tenths. 3 of those are the same. 1 of them is different. The no tenths is different. And whether we understand tenths or not, we can recognise that 4 of something is more than none of something. So the 3.04, there are no tenths compared to 4 tenths and the others. The no tenths is much less. That must in fact be the smallest of the numbers. 3.04 because it has no tenths. And again, we've used that one, we can cross that one off. But these others all had numbers that were the same in the tenth. They all had 4 tenths. So there's nothing really we can gain from that. We can look along to the next one now. We've got 4 hundredths, 0 hundredths, and, well, I guess that would be 0 hundredths as well. There's nothing in here. If we wanted to write the 0 in there to show that there's nothing, that would be okay. But we've got 4 hundredths, no hundredths, and no hundredths. Well, the 4 hundredths is more than the no hundredths. The 4 hundredths must be bigger than these two, because we've got 4 in there as opposed to 0 and 0. So this one must be bigger than the other two, which means this one, the 3.44, is going to have to go in this place here. It must be bigger than the other two, and the 3.44 we've used. We've got 2 left now, we just need to decide which is bigger. Well, we've got the thousandths column left to us. So we've got 4 thousandths in here, and again, no information in there. If we've got no information in there, we could fill that column with a 0 to show that there is nothing in there, and that's okay. We've not changed the number, we've changed the way it looks perhaps, but we've not changed the actual value of the number, and that's the key thing about adding these zeros. We can add zeros wherever we like if it doesn't change the value of the number. And we've not changed the value. It's still 3 units and 4 tenths. We've just shown that there are definitely no hundredths and no thousandths. And looking at that thousandths column, we've got no thousandths or 4 thousandths. The no thousandths must be less. The 4 thousandths must be more. So the 3.404 is going to go there, and the 3.4 is going to go there. And notice in particular with this one, but it's also true of any of these type questions, that yes, I have added the zeros on here to help me with these, but I've not put them in my final answer because the question said, write these numbers in order of size, smallest to largest. And that's what we've done. 3.04 first, then 3.4, a little bit bigger, tiny bit bigger, 3.404, then 3.44, and then 4.3, biggest of those. Yes, the numbers are quite confusing because they're all very similar, but the whole point of writing them in the grid makes them easier to compare because we can just go one column at a time.